This podcast is sponsored by the Norwegian Geotechnical Institute, NGI, your expert partner for offshore wind.
Hi, my name is Rasmus. I'm a geotechnical engineer. Back when I was a student, I wanted to build bridges. I guess, like all engineers. But then I discovered wind turbines. Today, I'm a specialist in the design of the foundations that support offshore wind turbines. No days are similar, because making the optimal foundation design requires the consideration of many different components. If you're listening to this, then you're probably, like me, fascinated by these massive engines of renewable energy. You might even be fascinated about how you can build a wind turbine that reaches almost 300 meters up in the air. Or you might just be fascinated by the global transition to clean energy that we'll all experience in the near future. That is what this show is about. Here, I'll be speaking to some of the world's leading experts about the history and science behind calculating and building wind turbine foundations. And of course, about how these foundations interact with the wind turbines above. So, get ready to hear what the best experts have to offer when speaking about big cylindrical open-ended steel pipes called monopiles and cylindrical steel buckets installed with suction called suction buckets. In this episode, I'll be speaking with Professor Byron Byrne, a cricket fan from Australia and also one of the leading experts in the world on monopile design. This is how he ended up as a professor in Oxford.
Having finished my undergraduate degrees in Australia, I took a gap year with work in Australia combined with playing cricket in England during the English summer. During that period, I became inspired to apply for a fully funded scholarship to study at Oxford, in which I was successful. That was the start of a remarkable adventure in Oxford. Having arrived for the PhD in 1996, I'm still at the university, where I'm currently involved in a wide range of teaching and research activities.
Byron is a research professor at the University of Oxford with a focus on advanced geotechnical design. This is a new position funded by the university, Ørsted, and the Royal Academy of Engineering as part of their research chair program. He has been leading the academic research group relating to maybe the most important research project concerning the foundation design of offshore wind turbines. And actually, he was also part of the evaluation committee for my PhD about monopiles. So I have to say that I was very excited when he agreed to speak with me about one of my own research interests, the monopiles. But before we start, it's good to know what a monopile really is.
These are large diameter steel tubes which are impact driven into the seabed and upon which the wind turbine sits. Monopiles are very large, with next generation foundations being perhaps 10 metres or even 12 metres in diameter and maybe 30 metres long. Perhaps 15 megawatt turbines will sit on top of these foundations. The wall thickness can be perhaps 100 millimetres or more, and the weight is very substantial. They can be easily fabricated with a good supply chain and are the preferred foundation solution at the moment for many offshore wind farms. An important engineering problem is to determine the optimal size of these foundations so that they can adequately support the wind turbine, so that it doesn't fall over, but not so over-designed that they contribute excessively to the cost.
This was Byron giving a short introduction to monopiles. What I really find fascinating with these piles is how the design has changed in recent years. Monopiles used to be designed using spring models developed for oil and gas platforms. But today, dedicated design methods have been developed for offshore wind turbines. This transformation from oil and gas to offshore wind, or from black to green, is one of the key subjects of this podcast. Here, Byron explains the transformation and the reasoning behind it.
One of the problems is that the offshore wind turbine pile is much, much larger than typical oil and gas jacket piles. Rather than being a diameter of up to 2 metres, they can be 10 metres in diameter or even more. And they tend to be much shorter in length by comparison to the diameter. A monopile might have a length to diameter ratio of between 2 and 5, whereas an offshore oil and gas pile might have a length to diameter ratio of maybe 50 or 100. In addition, an offshore wind turbine pile might be loaded about 5 to 15 diameters above the seabed. So reflecting the wind loading, which is acting at the nacelle, or the wave loading, which might be acting about 2/3 of the water depth from the seafloor. The loading conditions are very different to those typically applied to oil and gas jacket piles. Therefore, it's not clear that the design methods that have been developed for offshore oil and gas piles are necessarily applicable or scale up to the much larger diameter and more stubby offshore wind turbine monopiles. In particular, field monitoring projects in the 2000s identified that the design methods that had been used based on oil and gas jacket piles tended to be quite conservative. In particularly, natural frequency measurements were indicating that the system was much, much stiffer than had been originally anticipated from the design. Therefore, it implied that the amount of steel going into the monopiles was much more than it needed to be. These types of measurements underpinned the beginning of the PISA project.
As mentioned, I met Professor Byrne for the first time while doing my PhD, and I'm very happy that he took the time to have a chat with me about monopile design. It was my plan to visit the University of Oxford for a chat in person, but in these COVID times we ended up having a remote conversation about the development of monopile design in recent years, and especially about the PIile Soil Analsis project, commonly known as the PISA project. So what is the PISA project?
The PISA project comprised a very wide range of activities. The main objective was to change the philosophy of design, moving from rigid equation-based approaches, as encapsulated in previous design guidance, to more flexible approaches that incorporate properly the use of computational modelling, such as the finite element method. In this way, the design process can more properly be fine-tuned to site-specific conditions and therefore enable more robust design optimization. The insight in the project was developed from a wide range of connected activities: site investigation and laboratory element testing, numerical modelling, including sophisticated three-dimensional finite element analysis, theoretical developments, including the development of simplified design procedures, and a comprehensive medium-scale field pile testing campaign to validate the new design method. The key output of the PISA design method includes generic design procedures for wind farm designers, as well as sets of bespoke design equations. These enable simplified calculations to be completed, which have the fidelity of a more complex finite element calculation, but computed in a fraction of the time, covering a wide range of design conditions. The procedures specifically address the computational requirements for the engineering design team, where many load cases and design scenarios must be considered in a short period of time.
It is clear that the PISA project has had a large impact on the industry. It is actually very rare to see such a massive impact in an industry that is generally very conservative. But I think that besides the technical achievements of the project, the main reason behind the success of the PISA project was the high degree of industry involvement in the project. And this is actually another key subject of this podcast: how the industry itself has driven the main development of improved foundation design. The PISA project is a perfect example of how the industry and research communities have worked together to develop state-of-the-art methods.
The PISA project industry funding partners comprise 11 of Europe's main offshore wind developers, responsible for more than 75% of Europe's installed offshore wind capacity, and who are also involved more widely around the world. The industrial partners were critical to the success of the project. There were 5 major workshops throughout the project, which enabled critical feedback by the partner technical experts to be provided on the different stages of work. There was also an expert independent technical review panel to provide external scrutiny of the new methods and to scrutinise the output from the field tests. The work benefited substantially from this external feedback. The close collaboration, with the work focusing on soil profiles relevant to the UK European wind farm sites, ensures that the new methods are applicable to design of new wind farm developments going forward in the next decade or so. The 3 academic partners brought a range of different academic skills to the project. Oxford provided the scientific leadership on the strategic direction of the work, working alongside their industrial collaborators, and took responsibility for the delivery of a new simplified design method, including the theoretical developments, and all scientific aspects of the extensive field PIle testing campaign. Imperial College led on the 3-dimensional finite element modelling and site characterisation activities. University College Dublin provided support to the field testing activities. A very significant team of people from many different companies supported the project, probably numbering more than 100 in total. The key contractor for the work was Soccertech UK Limited, who delivered the practical side of the medium-scale field tests. The success of the project was underpinned by working with this wide range of enthusiastic and innovative partners. The PISA project is now complete, and we are further disseminating information from the work, but that is also fairly well complete. We have now published as open access on the web 8 papers in geotechnique. These will come out in a single issue of the journal in the next few months. We hope that this will enable the outputs and the learnings from the PISA project to be more rapidly picked up by the engineering industry, so that the new method can become embedded into design practice. A further paper on application of the PISA method to layered soils has just been accepted by Geotechnique and will be available more widely shortly. There have been a number of conference presentations, workshops and invited lectures, and in due course we aim to make any remaining findings from the PISA project more widely available, including work on cyclic loading that was completed during the project.
The impact of the PISA project is massive, and I do not think that the project has reached its full potential yet. Even as new publications and knowledge is added to the project, there still seems to be many different understandings of the PISA project and its impact. I often meet people who think that the PISA project only concerns new 1D models, but it's clearly more than that. I think one of the reasons for this might be that simple 1D model is the one that is most similar to the old school oil and gas design. For me, the game changer of the PISA project was the use of the finite element analysis, and how the results from this type of analysis can be scaled up and used for the foundation calculations for an entire wind farm. Once this becomes the industry standard, we are a lot closer to a transition from black to green energy.
The key of the PISA approach is that it has developed a systematic way in which finite element calculations can be incorporated into design across a site. The important outputs from PISA are the field test results, because they allow anyone to develop their own approach if they want and demonstrate that it works against those field test results. Of course, the PISA project has developed a new method which can be demonstrated against those field test results, and which allows the scaling up of the calculations to full-scale geometries and demonstrates that it can be used for a wide range of design calculations. The real advantage of the PISA approach is that you can scale the results from a few detailed finite element calculations to the whole site. The main idea is that you calibrate the simplified 1D engineering model with a small number of more sophisticated 3D finite element calculations. It is important that these finite element calculations involve parameters that bound the design space of interest. This could be geometry, it could be soil profile. The simplified model then interpolates fairly accurately within the design space to provide the more optimized designs for across the sites. These calculations can be completed in seconds, far quicker than would be possible with a finite element calculation. So it allows a significant amount of design iteration across a whole wind farm site. Once the final design iteration has been completed, a set of proof check finite element calculations can then be completed to verify individual foundation designs. So it is possible to design the whole wind farm site using the simplified method that is calibrated by a small number of finite element calculations at the start, and then at the end to benchmark a couple of the designs with bespoke finite element calculations specific for each design. Homogeneous sand and clay can be easily dealt with through the PISA design model approach. The key element with modelling of any soil is the selection and calibration of the constitutive model that is used for the underpinning finite element calculations. Therefore, sand and clay and layered materials can be completed within a holistic design approach. The method is structured so that for initial design, there are sets of rule-based equations. These were evaluated as part of the PISA project and currently exist for stiff clay, soft clay, and a range of sand densities. However, the design calculations can be further optimized for a specific site by completing a new set of finite element calculations to produce a new set of fine-tuned rule-based equations. Of course, once these new sets of equations are produced, they can be available in the future for concept design at another site with similar soil conditions. In this way, the PISA database of rules can evolve.
To understand the impact of what Byron is saying here about the PISA project, I would like to outline a few points on the complexity of monopile design. The traditional design method uses a spring model. Here, the pile is modeled as a beam and the soil as a series of uncoupled springs. The main reason why the spring models are so popular is that they are easy to use, easy to understand, and very fast. This is important when you have to run calculations for many wind turbine locations. Spring models are simple and do not capture the complete interaction between the soil and the pile. Traditional 3D finite elements captures these effects much better, but the methodology is complex and slow. What the PISA project has done is to combine the best parts of these two methods into one design methodology, where finite element models are run on a few locations and then a dedicated spring model is calibrated to these results. When the calibration is done, the calibrated fast spring model can then be used in the design flow for all locations. The new spring model is different from what has been used traditionally in oil and gas projects. The traditional model only had horizontal soil springs, which often are sufficient for design of long slender piles, but the new models have also introduced rotational springs. Imagine you take a stick and put it into the ground. The stick is rigid, but when you move the stick, you will see that a gap develops in the soil on the side that the stick moves away from. On the opposite side, the soil gets pushed in the direction the stick moves. This is similar to what happens when winds and waves move the monopile back and forth, and these effects are some of those that are addressed in the new model. Likewise, you can also imagine that the bottom part of the rigid stick moves, and this movement is also important, and it is now accounted for in the new 1D model.
what became clear is that for a short rigid pile, such as a monopile, that you not only had the Py springs or the lateral soil resistance reaction curves, but you had additional components of soil reaction reflecting of the physics of the rigid body rotating in the soil. And so additional soil reactions are added to the design calculation, including a distributed moment down the pile, which effectively is made up of the shear resistance on the outside of the pile, the vertical shear resistance on the outside of the pile acting across the pile, and also a base shear acting at the toe of the pile and a moment also acting at the toe of the pile. These additional components of reaction provide some considerable additional capacity to the pile, particularly when the length to diameter ratio reduces closer to 2 than 5. And in some instances, the additional components can account for up to 30% of the capacity of the pile. This might explain the observation for things like the diameter effect, that actually what was being observed was that the Py model was not picking up properly the physics of the problem, and therefore what was perceived to be the diameter effect was added into the calculation. But actually, by incorporating the additional soil reactions, the diameter effect is explicitly included in the calculation.
The additional rotational spring does not solve all problems. When a complex 3D soil-pile interaction mechanism is simplified into a simple 1D spring model, a loss of accuracy will always happen. I discussed this with Professor Byrne to try to understand the consequences of that simplification and why this is important in relation to the lack of interaction between soil layers. You may be wondering why this is important. In general, we can say that the estimate of the monopile response is important for the geotechnical design. But it is more than that, because the estimate of the monopile's response is also used in the load analysis and can therefore also lead to wrong loads. That's why it's important to understand the consequences of the simplification we do in the design process.
Almost all layering scenarios can be dealt with by application of the PISA design approach through calibration of the soil reaction curves using the homogeneous soil calibration cases. The assumption is that the layering profiles do not interact, so that 3D effects remain negligible. For most practical cases, this holds true, particularly for many practical wind farm sites which involve layering of stiff clays and dense sands. However, there are some instances where there is a strong interaction between the layers, typically where there is a very soft layer within a very stiff, strong material, and vice versa. In these instances, 3D effects become more important, and so more care is needed in the calibration of the models. And this would probably involve more finite element calculations.
What Byron is saying here is that because monopile design is driven by stiffness, the mobilization of soil is small, and the interaction between different soil layers is often insignificant. But one should be careful with alternating layers of stiff and soft soils. Earlier in this episode, I spoke about the importance of the correct monopile head stiffness for the load analysis. The PISA project has actually developed new nonlinear springs that can easily be used in the load analysis. However, quite often, only linear springs are used in the load analysis.
I think there's two ways that can be done. I mean, you can use linear springs if you're only really interested in the very small strain stiffness. But if you want to capture a wide range of behaviour, you probably need to go to more sophisticated models such as the PISA soil reaction curves.
This is something that makes me curious, because I'm not sure if this is the best way to model monopile responses in an aeroelastic load analysis. In reality, the monopile is repeatedly loaded and the stiffness changes when loading and unloading. My thought is that a secant linear stiffness may be a better representation of the hysteretic response, because the nonlinear elastic response would follow the initial loading but not the unloading. Instead, the linear model will model the loading and the unloading fairly well or bad. As a last part of the chat with Byron, we spoke about monopiles in the future. When I started my PhD, the diameters of a monopile were about 4 meters, and at that time we were saying that it could not get bigger. There were no vessels, no hammers that could handle sizes larger than that. That was obviously wrong.
At the moment, offshore monopiles have a diameter of about 10 metres. And next generation wind farms will likely use monopiles with diameter maybe 12 metres. In principle, there's no reason why the diameter could not increase to much larger figures, maybe 15 metres, maybe 20 metres. The limitation will be around fabrication of the monopiles and installation. But new techniques for installation, such as by using vibratory methods, might enable the prolonged use of even larger diameter monopiles. Of course, transporting the piles to the site will be important, but as you get to deeper water, it is possible that even larger diameter monopiles could be used. There's no reason from a geotechnical design perspective why a pile of diameter 20 metres and length 40 metres could not be designed to support a large capacity wind turbine generator. The PISA method could be applied to such a pile and would be robust. And in fact, the PISA design method can be applied to any type of foundation in which you need to do optimization. For example, it could very easily be applied to suction caisson foundations. The geometries are slightly different, the loading conditions might be slightly different, but the principles of the calibration process using finite element calculations and the adoption of a simplified engineering design model are the same.
If you're thinking, what is a suction caisson, and you would like to know more about this foundation concept and how it was developed, I would like to recommend the episode where I speak with Per Sparvik from NGI. Here we discuss suction caissons, or suction buckets as they are also called, and how they work. But back to the future of monopile research. The PISA project has had a big impact on the design of monopiles. But even if we have improved our design methods, there are still improvements to be made. One thing that the PISA project did not consider was the effect of cyclic loading. This is the new focus area for Byron and his research group at Oxford.
We have started a new project called PIle Cyclic Analysis, Oxford and Ørsted. This project aims to extend and embed the new design ideas such as PISA, but also for cyclic loading into routine engineering design. The new developments focus specifically on cyclic loading as the action of wind, waves and turbine operation impose significant repetitive loads on the structure and foundation. Currently, there are limited means for properly accounting for these loading within the soil structure response or integrating it into a computational model of the turbine to assess long-term performance. For the project, there are 5 strands of work, including advanced foundation modelling, further developing the PISA type ideas, calibration methods at laboratory element and model test scale, theoretical developments around the development of advanced plasticity models that capture hysteresis, ratcheting and rate effects, as well as multi-directionality, medium-scale field testing, and application to design. So Picasso is very much like the PISA project, but with a focus only on cyclic loading. We will be covering constant amplitude loading, single direction loading, multi-direction loading, and random amplitude loading such as might be experienced normally by a wind turbine. The field testing takes place later this year and into next year, and will involve testing at both a clay site and a sand site so that we can provide benchmark test results to both allow calibration of models, but importantly to validate a new approach that we've been developing that specifically captures cyclic loading at an element level, at a 1D modelling level, and at a macro element 0D level. We are fortunate in Oxford to have a wide range of other activities currently ongoing in the research group. We are partners in 2 centres for doctoral training, which represent major activities around the training of the next generation of technical leaders, in particular those with PhD degrees. The students undertake a structured training program over 4 years, combined with PhD research. We have already had 5 students complete our program, all now working in the industry, and currently have 13 students on the course, with a further 9 to start this October. This is a rapidly expanding activity, allowing us to develop further our interactions with the offshore wind industry.
I'm not sure why I find monopiles so fascinating. The geometry of the foundation is so simple. A hollow cylinder, and that's it. But today, it is the most popular foundation concept, and the one that most developers will consider when they start planning a new wind farm. But even though the geometry is simple, there is still a lot of complexity in the design, and there's also room for improvements. I think it's this dualism that still makes this popular foundation so interesting. The PISA project has demonstrated that you can use finite element models to predict the monopile response seen in the field tests. It has developed a new spring model and a new methodology to calibrate this model so it can be used efficiently in the design. But it's not done yet. These piles are cyclic loaded, and we need to address this when we do the design. For the past 40 years, the concept of cyclic stress and strain contours has been developed and used. And it is this methodology I use myself when I design monopiles today. This can easily be used together with many of the ideas from the PISA project. And I hope that Byron and his group are looking in that direction when they develop new procedures as part of the PISA project. I hope you have enjoyed this episode and that it has sparked an interest for the other episodes on bucket foundations. A big thank you to Byron Byrne for joining me in this episode. You have been listening to Offshore Foundations, a geotechnical podcast about offshore wind turbine foundations. My name is Rasmus Klinkvort. Thank you for listening.
This podcast was brought to you by NGI, the Norwegian Geotechnical Institute, your expert partner for offshore wind.